Hi everyone. I'm here today to talk to you about the other half of the language that people sometimes overlook, the standard library. Many people don't recognize that C++ is really divided into two halves. You've got the core language, which is pointers and integers, floating point, and then the standard library, which is really the higher level abstractions on which users actually build their programs. Today I'm going to cover some magical things we do in the standard library. Then I'm going to reveal a couple of secrets that have not been announced before. So first, these magical things that we do. Why are we using native code in the first place? Well, there's a few reasons I can think of. It's easy to sort of forget that your computations are going to run on actual hardware. But in the end, they do. And you really can't ever forget that fact if you're going to write high-performance code that needs to be robust. And there was a period of time in the early 2000s or so, which was coincidentally when I was learning how to program C++, when it seemed like computers were just getting faster and faster and bigger without limit. And a lot of those trends have actually tapered off. So when it comes to like a memory usage, space, it seemed that today computers are they've got a gig of RAM that's going to be 2 gigs, 3 gigs. We don't need to worry about memory consumption. And now we're deep in the 21st century, and we kind of do. We've got small devices like phones and tablets and consoles. How much RAM do they have? Well, about 512 megs right now. That's not so much. I can think of lots of things that I would like to stick in 512 megs of RAM. But I don't want to run out of memory. I don't want bad Alec. Let's leave aside desktops for the moment. Many of you may be writing server applications. Servers are gigantic, 64 gigs of RAM, terabytes, what have you. But think about how many users they need to service. Tens of thousands of users. Suddenly, all of those 64 gigs of RAM don't seem so big anymore. And even if you have a very large machine, maybe you're using virtualization, which is the next big thing, cloud computing. When you take a large physical machine and slice it up into lots of little servers, maybe those servers only end up with half a gig of RAM, a gig of RAM. Space usage is important even on the server space. Now, desktops are interesting because you've got relatively large systems, 4 gigs, 8 gigs of RAM, and only 1 or 2 concurrent users. But think about the memory hierarchy. Yeah, I mean, memory is big, but it's also relatively slow and far away when you're thinking about how fast processors have become. The caches are very fast, but they're also small. Like level 3 cache is like maybe 8 megs. Level 2 caches are like 256 kilobytes. Level 1 cache is like 32 kilobytes. These are extremely small numbers. And yet, if you can get your program's core inner loop to fit within these relatively small magic numbers, everything becomes so much faster because you don't have to go all the way out to main memory. So focusing on space usage is important. Well, what about time? Again, back in the early 2000s, it seemed like processors were constantly getting faster, 10 gigahertz by the end of the century. Yeah, that never happened. Instead, they sort of peaked out at frequency about like 4 gigahertz is the limit. And instead, we've been getting more cores. So while the frequencies are continuing to improve somewhat and instructions per cycle are improving somewhat, the amount of single core perf we can expect on a desktop is really limited by power at this point. And even then, we've hit like 100 watts, 130 watts of TDP. The amount of time in which we have to do things is looking less and less when you need to constantly display fast and fluid animation at 60 or now 120 with stereoscopic 3D frames per second. That's like 16 milliseconds or 8 milliseconds, and bam, you got to go put up another frame. If you have a program that is very conservative about how much time it spends, then you can do more work before you need to go put up that next frame. And finally, we've got these two limits of the hardware, space and time, but there's an even more fundamental limit when it comes to working with the world of atoms, and that is that you, the programmer, are made of atoms. The problems that we have to solve as programmers are just constantly getting bigger and bigger. Programs that we were able to write in the early 2000s were relatively small. Now they need to go talk to a database, they need to be multi-threaded, they need to be displaying DirectX or OpenGL, they need to have extremely complicated data structures, talk to tens of thousands of users. The problems are just getting bigger and bigger. But our brains are not. Yeah, we get more experienced over time, but the amount of little twists and turns we can keep in our head is really constant. Bigger for some people than others, but the problems just keep getting bigger. So in order to write stably working programs, we need tools that allow us to work at a higher level of abstraction. Break a problem into component chunks, load it into our head, get it right, set it aside, load the next chunk in, and then get that right. And the primary tool for doing that is libraries. You can stack libraries on top of each other, the CRT, the STL, Boost, higher level libraries specific to your domain. If you're a large company, you may have company-specific libraries. And the STL is sort of the one that is right above the CRT and is one of the first users of new C++ 11 features. Basically, everybody here in this room is going to use the STL, some more, some less, but there's really no avoiding it. And that means that the STL has to service a vast majority of users while retaining extremely high performance and extremely high levels of correctness. If there's a bug in the STL, like say VC10RTM stood string leaked 16 bytes of memory, that's really bad. All of your programs leaked lots of memory until you patched to SP1. I feel really bad about that one. Yeah. So these are the concerns that we have to deal with as standard library developers. I'm going to hit each of these. In space, we've got an optimization that I did in make shared that saves memory. In time, there is a new form of putting things into vectors. And as far as abstraction goes, I teased in the abstract that there are ridiculous things going on in stood pair, which used to be the simplest class in the world and now is rather complex. But it's for a good reason. And we'll see how that works. So make shared. Shared Putter was introduced in TR1. It was originally designed in Boost, made its way into TR1, and then became part of C++ 11, and that's when Make Shared was added. And there's really 5 different fundamental ways you can construct a shared putter. I've outlined them here. There's the plain vanilla way of you new up a T object, you give it some args for its constructor, and then, because owning raw pointers are leak-trosity, as we've seen in Bajarn's presentation, we immediately give it to an RAII resource manager shared putter. But shared putter is also customizable. In this case, if you're using new, you want the pair delete. But maybe instead of saying new targs, maybe I need to call a special API that's maybe newing up a font or allocating a font, and it needs to be matched with a paired resource destruction function. The default shared putter is just going to pair it with delete, but I can give it a custom deleter that will invoke that function or potentially function object storing state on the pointer when it's time to be destroyed. I can also give it a custom allocator to control how the shared putter allocates its own internal data structures. And then there are these new ways, make shared and allocate shared, that construct an object from arguments and create a shared putter to it all at once. This is convenient because you'll notice that I only have to mention the type T once instead of twice. It's less typing. Notice how the line is shorter. And I only have to say auto. And then there's other constructors on shared putter that I won't go into. These are not fundamental ones. Now, the most interesting thing about these methods of construction is what is not there. Imagine stood vector, which has been around since 1994. If you want to customize the allocator type, you have to say vector T myalloc T. And then it will use that provided allocator to retrieve and get rid of memory. Shared putter takes custom deleters and allocators, yet that's not apparent in the type. It's always returning a shared putter T. This is achieved through a technique that's called type erasure. And this was considered very important during the design of Boost, because that means that if an API takes a shared putter T, you can give it something that's paired with a custom deleter, and the API doesn't need to know that. Whereas if you've got something that's taking vectors and somebody hard-coded it to say, I'm taking a vector of T angle bracket, and then they didn't allow a customizable allocator, then you're just out of luck because there's a type mismatch. Now, type erasure is sort of erasing a custom deleter and allocator type. It's also being used for make shared. It's not visible because you would think, oh, make shared doesn't have a custom deleter allocator. But behind the scenes, it's doing something clever. I'll show you how that works on the next couple slides. So here is a diagram of the representation of shared putter. Now, One of the things when using a library is you don't really want to know too much about its internals, because you don't want to make non-portable assumptions or assumptions that are going to change over time. Some level of distance is good, but it's also always good to just have a vague idea of the representations of things you're working with. Like, it's critically important to know that a std vector is a contiguous block of memory and a std list is a linked list of non-contiguous elements. That both affects correctness guarantees and performance. You know when one is appropriate. So shared putters representation, I'm outlining VC10's implementation here. Other implementations will differ. We'll see how that works. A shared putter is the size of 2 raw pointers on x86. That's 8 bytes. And one pointer is a direct pointer to the object. This is nice because when you dereference a shared pointer, it's 0 overhead. You just follow that underscore putter, find your object, done. You don't even need to add an offset. But shared putter is a non-intrusive reference counted smart pointer. And that non-intrusive part is great. It means that you can own anything with a shared putter and you don't need to teach it that it's going to be reference counted. But shared putter needs to store a reference count somewhere, and like shared putter int, you can't jam a reference count into an int. It doesn't have a space for that. So the shared putter needs a separate block of memory. We call that the reference count control block. Here I've outlined it as ref count tie. It's templated on the element type. It stores both the strong ref count, the number of shared putters pointing to it, also weak ref count, because we support weak putter, and it has an extra member here internally, underscore putter. So the way that this works with type erasure is that the shared putter has a pointer to a non-template base class. Here it's ref count base. And this is a polymorphic base. We've all used that inheritance. And it stores the strong and weak ref counts because those are universal to every possible shared putter. And what it really points to is this ref count tie block that's templated on the element type. So at runtime, we've erased that type information because we've just got a pointer to base. But we're remembering it through the magic of virtual functions. And the ref count needs a pointer to the object as well. This may seem redundant at first, but think about what happens when all of the shared pointers to an object die and the object needs to be destroyed. Well, we need to invoke a virtual function on the ref count control block and say, hey, it's time to get rid of this object. The ref count control block needs to know what to delete, so it needs a pointer to the object itself. Hence the apparently redundant pointer. I've shown the other control blocks we have there for custom deleters and custom allocators. So now I'm going to switch and show you what make shared and allocate shared give you. When you use make shared tie or t and then give it some constructor arguments, it constructs the object within its reference count control block. This is one dynamic memory allocation instead of 2. That's great because we only have to hit Windows heap alloc once, potentially take a lock, go into kernel mode, do expensive operations. Also, we're saving additional invisible allocator overhead. And we have increased locality. And the shared putter doesn't need to know anything about this because of the virtual functions that we're using internally. Like Bjarne said, inheritance really is overused often. In this case, though, it's being concealed within the shared putter's implementation. If I didn't tell you that the shared putter was using virtual functions internally, you wouldn't know. You would just see auto sp equals make shared t arguments, and internally it's using inheritance, but externally it just looks like a template. They're actually working together. So in addition to cramming the object into its reference count control block, there's a space optimization that I did when I rewrote this, and we're not storing that extra underscore putter. Here I've put the plain vanilla control block on the upper right, you can see. I'm not storing the underscore putter. Why? Well, when it comes time to destroy the object, I call this the we know where you live optimization. We know where it lives. It's just in the storage. It's an aligned storage data member. And we can just go invoke a destructor explicitly, which is very low-level code, but it's important in a standard library. Not storing that pointer is actually a good optimization because it saves space. And I did measurements on Win7. Win7 is important because Vista and above operating systems automatically use something called the low fragmentation heap. That's very friendly to large numbers of small identically sized allocations like linked list nodes or reference count control blocks. My measurements include any invisible allocator overhead, but they specifically exclude the shared putter itself. That cost is paid no matter what, even if the shared putter is null, and I wasn't interested in that cost. Plus, we know its size. It's 8 bytes on x86 or 16 on x64. So on x86, the plain vanilla way of constructing a shared putter, where you new up an object and give it to a shared putter and then it'll delete it afterwards, that costs 40 bytes. This is just a shared putter int. So it's not super cheap, but it's still relatively small. And this was the same throughout the 3 implementations I tested: VC10, SP1, Boost 148.0, and GCC 461. Now, if I use make shared, with Boost and GCC, it saves space, 8 bytes. On VC, we save a further 8 bytes. It only costs 24 bytes. That's almost half the original space usage. And that's coming from not storing that additional pointer. Boost and GCC's implementations are less efficient. On x64, the numbers are even more dramatic. 48 bytes goes down to 32. So we're saving 16 bytes for VC and SP1. And curiously, for Boost and GCC, there's actually no change in memory usage. I believe this is because of the way that the allocator overhead works. It's probably aligned on 16-byte boundaries. I can't see what it's doing internally. I can only observe the measurements. So even if you're working with an implementation that doesn't save as much space as VC's does by the we know where you live optimization, it's still good to use make shared whenever possible, because they are avoiding those 2 dynamic memory allocations going down to 1. That's good. It's just that saving extra space is also good. So if there are any Boost developers in the audience or watching, you gave us the shared putter interface. Thank you. I'm giving you back on optimization. Please implement this. Just get rid of the pointer, please. So yes. And imagine how many shared pointers you might have in a program. Maybe 10,000, maybe 100,000 if you have a lot. Saving 8 bytes per shared pointer, that's a lot of memory. And the best part is this optimization is for free. This is the sort of thing that I worry about as a standard library developer. In ordinary application code, yeah, it could be considered premature optimization. But something that is as widely used as the standard library, we can engage in a little premature optimization. It's not evil for standard library developers. So moving on to time, let's think about move semantics, which have been mentioned earlier. One of the great things about C is its value semantics. If you've got an int and you copy it, the source and the copy and the destination, they're separate objects. They can be modified independently. They're easy to reason about. C++, inheriting C's wonderful memory model, had a sort of downside because it introduced objects of class type that can have expensive copy constructors. So we're still preserving C's wonderful value semantics, but we're getting unnecessary copies in some cases. This was really the biggest downside performance-wise of C++ 9803 is that it liked copying objects a little too much. Copying does a lot of work. It needs to dynamically allocate memory. Like I said, that hits on Windows heap alloc, potentially taking a lock, doing other expensive operations. If you're copying a vector of T, you need to copy all of its elements. Maybe it's a vector string, and we've got to do more dynamic memory allocations. We've just been taught as programmers that, hey, we want to avoid copies. Even for something as relatively cheap as shared putter, copying it introduces an interlocked increment, and that's not free either. That's like 12 cycles to 80 cycles as compared to like a half a cycle for a plain increment. So move constructors are great. If you upgrade to a compiler like VC10 or recent versions of GCC that provide move semantics and take advantage of it in the standard library, you will notice that your programs automatically speed up for free. That is the best kind of speed up because move constructors avoid so much work. But it's still not instantaneous. If I've got, say I'm moving a vector, just a vector of int, what does it need to do? Well, it needs to copy pointers to the memory block, and then it needs to null out the source pointer, telling the destructor, hey, you're empty, you don't need to destroy anything, and potentially copy other plain old data. If my vector's representation is pointer plus size plus capacity, I need to copy over the size and capacity. Those are size t's or whatever, but I still need to copy the bits. So it's going to be 3, 6 instructions, something like that, but 6 is more than 0. So what could be faster than a move constructor? Literally nothing. And that is what has been added to the C++11 standard library. It's called emplacement. So here I've got some example code with a vector pair of strings. Instead of saying v pushback, make pair, and then give it a string and an int, now with C++11 I can say v emplace back and then directly give arguments to construct an object of the vector's element type. In this case, it's a pair string int, so I just give it a string, potentially a string literal or a consecure star or another string, and then an integer. and I will directly construct an object at the back of the vector. I don't need to copy, and I don't even need to move. This is as fast as you can possibly get. Ordinarily, this doesn't make a huge difference, but in a tight inner loop, it might. And it also can be more convenient. For example, here I didn't need to say make pair. The vector already knows that it's a vector of pairs, so I can just say v in place back, and it's actually less typing than a v pushback. This has been applied throughout the whole standard library. Vector, list, forward list, like anybody uses that one. Map, set, unordered set. They all have emplacement versions of things that are either called push or insert. Map has in place hint, things like that. And this has all been implemented in VC11. In VC10, if you look at IntelliSense or whatever, you will see that they do have in place member functions, but only for one argument, which was not so useful, sorry. In VC11, we've gone and simulated variadic templates enough to provide up to infinity arguments, infinity being 5 by default. You can increase that to 10 by defining variadic max. The standard library still does not go to 11. We need real variadic templates. But up to 5 arguments, that's pretty good. So that's emplacement. And finally, I was mentioning abstraction. One of the ways to write highly abstract programs is to be able to work with data structures. And the simplest data structure you can imagine is a pair. I just want to pair two things. Pair in C++ 9803 was a very simple data structure. It had public first and second members, a converting constructor, and that was basically it. As move semantics and R value references and perfect forwarding were applied during C++ 11's evolution, the standardization committee broke pair. They broke totally conformant, totally legit C++ 9803 user code. And this was broken, I've got the working paper up there, as late as February 2010. That was just a year ago. No, 2 years ago. Sorry, it's 2012 now. That was relatively recent. And in fact, when we shipped VC10, this was still broken in the working paper, and we just had to ship our implementation. So if you compile code with the VC10 SP1, here I've got a pair of X star and double. I don't care about that second type. And I construct that pair from a literal 0, or the macro null, which expands to 0. That will fail to compile, according to N3000 or N35, the working paper at the time, with an error message saying error cannot convert from int to X star. Why is it complaining like this? Well, the working paper added a perfect forwarding constructor to pair, and this is good. If you've got a pair of string or a pair of vector, it allows you to perfectly forward arguments and potentially move resources. That's good for efficiency, and the problem is that null is a horrible abomination. It's so bad, so terrible. And why is it terrible? It's because it has the wrong type. The type of the literal 0 is int. Int is not convertible to a pointer. So if you pass it to a perfect forwarder, what happens is that the perfect forwarder here deduces u to be int and then tries to take that int and construct an X star. Oops, type mismatch, cannot compile. The only reason this usually compiles is because by special dispensation in the standardese, the literal 0 is convertible to any pointer. This is a rule outside of the type system. When you subvert this type system, bad things happen, like this. Now, if you use null putter, things are okay. When we actually discovered this during VC10's development in the standard library, we looked at this and we're like, this is breaking, totally conformant user code. Can we fix it? No, it's not yet fixed in the working paper. Should we try to hack around it? No, pair is too widely used. We don't want to break it. I've broken bitset before by adding extra constructors. I don't want to go there for pair. We fixed it. And so instead we went back to our compiler front-end developer, Jonathan Caves, and we said, hey, could you give us this null pointer feature? And so he implemented that. And in VC10, if you give null putter to pair, that works properly because null putter's type is null putter t, and that's perfectly forwarded along. Yet it's bad to break that user code that uses null, even if null is pretty evil. So how did the standardization committee fix this? Fortunately, they did before the final stamp was put onto C++ 11. And they added an extra little remark section. Here I've got a working paper equivalent to the official C++ 11 standard. They added this sort of cryptic remarks. Here they're instructing implementers like me in Dinkumware to do something special. What they say is, if U is not implicitly convertible to the first type of the pair, or V is not implicitly convertible to the second type of the pair in this perfect forwarding constructor, this constructor shall not participate in overload resolution. And when they say the specific sequence of magic words, that's a directive to the implementers. And they say, you need to use something called Safini, powered by the enable if template in type traits or equivalent machinery, to disable this constructor from overload resolution whenever this condition applies or doesn't apply. Basically, it says, pretend that this perfect forwarding constructor did not exist if its body would not compile. And this is useful because now in VC11 and in C++11, if you try to construct a pair of pointers from the literal 0 or the macro null, this will compile now because the perfect forwarding constructor will instantiate itself with template argument deduction. It'll find U to be int and will notice, hey, int is not convertible to x star. The body of this constructor could not compile at all. So instead of emitting an error, I'm just going to pretend that it didn't exist in the first place. The compiler takes a step back and just snips that constructor out entirely. There's one constructor remains, though, and that's the original C++ 9803 constructor that takes a hard-coded const t1 ref, in this case const x star ref, and the rule that the literal 0 is convertible to a pointer can jump in and say, yes, I can compile. Nullputter still compiles. So even though 0 null is acceptable now, don't use them, please. They're terrible. Nullputter's way better. Basically, every time you would write nullputter. If it compiles, great. If it doesn't compile, you are about to misuse null anyways. I've seen it used as a character constant, as an integer. I've seen int n equals null. No, don't do that. This was within Microsoft's own sources. So please use nullputter. Consider a function like makeSharedT that takes an arbitrary number of arbitrary arguments and forwards them along. That does not have a corresponding fixed version that will handle null properly. So if you have an object that takes pointers and you try to make shared T of that type and give it the macro null, that will never compile. You must use nullputter. But at least if you've got existing code bases that were broken by VC10, they'll work in VC11. That's very nice. This has also been applied to tuple for the same reason. Now, you might say, yeah, this is great. You broke some code and then you fixed it. Way to go, committee. What is this really buying us? Well, it's actually buying something useful. This is going back to the abstraction I mentioned. Here's a very simple overload set. Imagine that you're a newbie on, like, I guess, day 5, and you're willing to write some functions that are taking pairs. You've been introduced to the standard library. And I've got a couple functions here, one meow taking a pair of ints, and another meow taking a pair of strings, and they just print them out and do something different. And then I have a couple of very innocent calls. One saying meow make pair of a couple integers, and the other one saying meow make pair of a couple strings. It's obvious which overloads I want to be selected. This code is not evil or bad or wrong in any way. Surprisingly, though, this is not valid in C++ 9803. And if you try to compile this with either VC9 SP1 or VC10 SP1, you get an error. It says error, meow, ambiguous call to overloaded function. And this is omitted for the second call, make pair with the string literals. Why is this? Well, if I say make pair string literals, then what I get back is a pair of const-char star. Pair of const-char star is not the same type as either pair of int or pair of stood string. But pair has a converting constructor. In C++ 9803, it had a converting copy constructor. And what the compiler in the language will do is they'll say, user's got a pair of const-char star, not the same type as any of these functions, but could I convert things? Well, let's see. Yes, I could convert to pair of stood string. Does a constructor exist that can convert to pair int? And that constructor's signature exists, even though the body will totally not compile. Just the fact that the signature exists means that the compiler sees two possible conversions and it can't decide between them. All user-defined conversions are equally good. The compiler is not psychic. It cannot guess your intention. If it sees two possible conversion functions, it's going to throw up its hands and say, hey, programmer, I need help. I don't know which one. Hence, you get the ambiguous call to overloaded functions. And yet, in C++11, this now compiles. The int1 goes to the int overload as before, and the const-char star pair is now converted to pair string unambiguously. And this is caused by the committee adding the exact same language to pairs converting copy constructor and converting move constructor. They say this constructor shall not participate in overload resolution if these constructors would never compile. This means that they will be removed from consideration in the case of trying to convert a pair of const-char star to pair of int. So this is great. This helps users who are writing very innocent overload sets, and they don't need to know anything about this. Things just work. They don't need to know about substitution failures, not an error, or templated move constructors, or anything like that. And yet the STL is working behind the scenes. The implementation is quite complex. I'm hiding it from you here just to save your sanity. It's got underscores everywhere. One final note, it's not perfect though. And this is just to show you that C++ does have lots of subtleties. Imagine that you've got an inheritance hierarchy, base, derived, and more derived. You've got two Plano functions, one taking base star, one taking derived star, and then you've got a more derived star argument. Which one should be selected? Well, more derived star is convertible to both base star and to derived star. But the core language has a special rule. It says, going to derived star is less of a leap. I'm going to use that conversion as the programmer expected. The more derived one is more appropriate. But if you've got pairs here, pair of base star, pair of derived star, and pair of more derived star, notice what happens. Because the pair of more derived star is convertible to both pair of base star and pair of derived star, it gets past this Fine check. It says, oh, it is convertible, so I'm going to let this constructor exist. And they would both compile. And then there's no rule to tie break between them. They're both user-defined conversions, and all user-defined conversions are considered equally good. So in this case, you would still get an ambiguity. But in the case when you've got pair of int versus pair of string versus pair of completely ridiculous pointer, that's considered unambiguous. So it's not perfect, but it's pretty good. So that's the last thing I want to mention about magic. Now on to secrets. I mentioned that there are secrets that I'm going to reveal. The first one relates to futures, which we've seen a couple times, and it's on the back of the t-shirts that were handed out. We are shipping in VC11 implementations of all of the threading futures headers that were not present in VC10. We would have loved to get them in, but there was just no time to add more standard library features. We have that time in VC11. And in VC11 beta, and even better in RTM, condition variable, future, and mutex headers, they're going to be powered by the concurrency runtime, which was implemented by our parallel computing platform team and already shipped in VC10. Concert, it would take a whole nother presentation to go into what it does, but it's a highly efficient cooperative blocking, cooperative scheduling implementation, and that you can read about in MSDN. There's a whole node of topics about how they work their magic, and now that's going to be powering stood future and condition variable and mutex. Well, what does this buy for you? This means that if you spin up a bunch of futures, maybe 10,000, it will not spin up 10,000 different physical threads. That would be very bad. Instead, Concert will ensure that it spins up only as many threads as is needed to saturate your user's machine. And notice I said user's machine. That's important. Imagine that you're a dev, you're running on a quad-core machine, and your user's only running on a dual-core machine. Concert will saturate that dual core. Now, flip it around. Maybe you're a dev with a quad-core machine, but your user is running gigantic hardware, maybe a 2-socket system with 16 total cores. Concert will scale up and spin up enough threads to saturate all those cores. This is especially important if you write code once, you compile it once, and then your user uses it 3 years down the line. Concert adapts at runtime and partitions that work for you. And in the standard library, we would love to get Concert to do that work because they've already implemented that. Now there is a caveat. In VC11 beta and continuing in RTM, all of the multi-threading headers will emit errors if they are compiled under CLR or CLR pure. This is halfway for a simple reason. That's because Concert is not supported for C++ CLI. And that was true in VC10. It'll remain true in VC11. We're additionally blocking Atomic and Thread under CLR pure A because Thread uses mutex in its implementation. And B, getting them to work properly under CLR would be way too much work for this product cycle. Sorry, I would love to give you all those goodies, but you'll have to settle for them in native mode. I'm not saying that we're going to never support the multi-threading headers under CLR pure, just not for this release. But hey, this is going native, so hopefully nobody will complain. Yeah, so that was the first secret I had, that Future is powered by Concert. So before I get to the second one, let's look at Future in action, or look at the back of the t-shirt that was just handed out. Here is some code. I actually wrote this example, and it's an example of what will happen when you've got a reasonably conformant C++ 11 compiler and standard library. What does this code do? Well, it has a function to reverse a string, and I create a bunch of asynchronous tasks to flip 3 different strings. I put them into a vector, and then I print them out in order. If you can read the strings backwards, you can see what it says. So how many C++11 features am I using here? Well, let's walk through them in order. Vector of future string, future is new to C++11. If you have a very sensitive eyes, you will notice that I'm using right angle brackets. There's no space between those angle brackets. I always forget of that as a C++11 feature because that's been implemented since VC 8 in 2005, but it is new to C++11. It's surprising how primitive C++9803 was. It couldn't even handle angle brackets without spaces, but now it can. Let's see, async, that is a standard library function. It lives in the future header. Oh, and I'm using lambdas. That's a big feature in C++11 that was implemented in VC10. Flip, that's an ordinary function call. Oh, look, I've got a range-based for loop. That's new to C++11, not supported in VC10. And I'm using auto. I'm saying for every element, E means element, in this vector, I want to print out getting the futures value. Here, it's a vector of futures, and it has a getMember function. If you are very observant, I'm using a 7th feature, and that's because I wrote flip taking string by modifiable value. I'm a standard library developer. I know about efficiency. I know when I'm observing objects of class type that I should probably take them by const reference. So why it's physically painful for me to write functions taking by value. I'm like, oh, I've got a copy there unless it's taking an int. Yet I wrote flip string s. Why did I do that? Well, because of move semantics. Imagine that I wrote string flip taking const string ref, and I give it an L value, a named variable. Well, I have no choice. I'm going to bind a reference to that, and then I'm going to need to create a copy, because I can't go modify the original. I'm going to reverse the copy in place and then return it. So for a named variable, I would incur a copy. What if I was taking const string ref and I gave it an R value, a temporary? I would bind a const string ref to it, and then at that point, I wouldn't know whether I was bound to a named variable or a temporary. So I would have to create an unnecessary copy, reverse it in place, and then return it. That's undesirable. By writing flip taking modifiable string s, I actually save a copy in that temporary case. If the source is a named variable, what happens is that it's copied into my local, my function parameter, and then I reverse it in place, and then I return it by moving it out. So I still get a copy, but that copy was unavoidable. If, however, the source is an R value, I move it into the function parameter. That's just a couple of instructions. Then I reverse it in place because nobody can see my function parameter, and then I return it by a move. So I have downgraded or upgraded a copy into a couple moves. So it's still, the guidance is still, if you're writing something that's observing, you should probably take by const ref. But in the case when you're going to make a copy anyways, consider taking by modifiable value like this. So what does this print out? Well, if you read backwards, it prints out, hello, GoingNative 2012. So now I have a question. I want everybody to vote. Do you think that this is guaranteed to print out hello GoingNative 2012, or could it print complete garbage? Who thinks that I've got a guarantee that it's going to print this out? OK, a few people. Who thinks that I could potentially get garbage, like printed out in a garbage order? The answer is that this is actually guaranteed to print out hello GoingNative 2012. And why is that? Well, it is true that the asynchronous function calls can be executed concurrently, simultaneously in any order. This can actually use up to 4 cores, 3 for the flips, and then 1 for the main thread, which will still be proceeding on. However, each lambda returns its result into a stood future, which is sort of a handle to a result that will exist in the future but doesn't maybe exist yet. I am pushing those lambdas through the async function into my vector futures in a specific order. And then I iterate through the vector in order, and I grab each future saying, OK, I don't care if you computed it already, or you haven't gotten around to it yet, or you're in the middle of doing it. Please block and give me the result right now, and I read them in a deterministic order. So even though they're computed asynchronously, I print them out in a guaranteed order, hello GoingNative 2012. Of course, I would have a data race if flip did anything like modify global state, but as I've written it, it doesn't modify anything outside its function itself. So this is code that will exist 20 minutes in the future. So now, it is time for the reveal. I use the range-based for loop there. And there was actually a blog post, which I had several months ago, revealing the level of C++11 core language support in VC11, and the range-based for loop and a bunch of other features were not among them. The reaction was somewhat not pleased. People expected that they would get goodies, and they didn't get as many goodies as they wanted. I mean, certainly as a library developer, I would love variadic templates. I suffer enormously in their absence. We make do with macros, which are evil. And when this happened, we went back and we said, what can we do about this? Well, the range-based for loop will be supported in VC11. You will be able to use this in production code. But wait, it gets better. It's not just going to be supported in VC11 RTM. It's going to be supported in VC11 beta. When the beta comes out, you will be able to use it. This is all thanks to our compiler front-end developer, Jonathan Caves. When he heard about how people were unhappy with the level of core language support, he actually took his own personal time on weekends and wrote up this feature from scratch and got it checked into the compiler. He didn't have to do that, but he did, and I'm very thankful. So that's why I'm giving him all the credit. Thank you, Jonathan. He's here in the audience, but he's not standing up. He's very modest. He even said, "Oh, don't put my name in the slides," but I wanted to give him credit. Don't mail him or anything. He was nice. Don't bug him. Bug me. And now we can't just go check crazy stuff into the compiler whenever we want, although sometimes the compiler devs would love that. Things need to be tested. And one of the reasons why we didn't initially plan, or management, I'm not a manager, didn't initially plan to put the range-based for loop in VC11 is that our QA team, our test team, was just completely filled to capacity, testing the whole new front end and all sorts of things. And they literally had no more capacity to test. So what do? Well, we got a fake tester. We got some guy who's not on the compiler team and not a tester at all to write a bunch of tests. Now, the tests he wrote are real tests. They were actually checked into the automated harness. They're passing 100%. That's good. He forgot to test things like control flow until the very end, like break and go to and continue. He remembered, though, at the very last minute, and they work, which is good. He even recruited, okay, it was me, recruited a few minions throughout the company, Ryan, Ahmed, and Pavel, who contributed additional useful tests and found some less than stellar diagnostics, which Jonathan was able to improve. And then finally, we got all of these tests reviewed by actual testers on the test team. Reviewing is faster than writing tests themselves. Olsey and Andy, who suggested further improvements in breaking up the tests into good chunks. So this is basically production code ready to be used. I have tried to break it every way I can, and as I'm a professional compiler breaker. I'm not a tester, but I break the front end all the time. So it survived my beating on it. Now, C++ is a complicated language, and I certainly haven't tested everything possible. There's probably more bugs waiting there. That's why we're shipping in beta so that we can get even further experience. If you find bugs, report them through Microsoft Connect. But as it stands, I think that it would take extremely obscure code. It works in the vast majority of situations. Now, you might be expecting that it's the holidays. I'm just going to give you features left and right, but I can't give you everything. One of the things that will not be supported in beta is IntelliSense. If you're trying to write the range-based for loop in the IDE in VC11 beta, you're going to get red squiggles. It's going to say, I don't know what you're writing. What is this colon doing here? That's because the IntelliSense front end is different than the compiler front end. It will support the range-based for loop in VC11 RTM. But as of beta, you're going to get red squiggles. That's because our IntelliSense front end is developed by the EDG company, and we only told them that we were doing the range-based for loop like 4 days before beta lockdown. They had no time to react to this. It's not their fault at all, but they're going to implement it by RTM. We felt it was important to just get the feature in the actual physical compiler. So now I want to go over how the range-based for loop works. I'm going to throw a little standardies at you, color-coded for your convenience. If you write for and then put a declaration there and then colon and then a range expression and then a statement, the standard literally says that it spams out a little code here. This code looks sort of scary at first, but it's doing something very nice, very extensible. And what it does is it takes your range expression and binds it to a named range. It actually wraps it in parentheses, so if you put a top-level comma operator in there, it doesn't explode horribly. I tested that. VC handles it perfectly, and it actually broke GCC. I found bugs in GCC comparing it to VC. That was fun. And then it gets a begin and end from the range. We'll see how that works. Iterates through them with a plain loop, and then dereferences the iterator and stores that in whatever declaration you give it. And then it executes the statement for each element. And in fact, the standard is even more permissive than this. You can put, in C++11, braced initializer lists in place of the range. So you could say for int I colon left brace 11, comma 22, comma 33, right brace, parenthesis. And that'll work in C++11, but not in VC11 because we don't have initializer lists. Sorry, that would be a whole other major feature. So that's not going to be in RTM. But everything else that the range-based for loop is capable of has been implemented. So what is this crazy, oh, and by the way, these double underscore variables, they are for exposition only because the standard has to give names to these things. They don't really exist. The double underscore means it's totally internal. So don't attempt to refer to them. They're in diagnostics, they're actually like $1. So what does this auto-ref underscore range thing do? Well, auto is powered by template argument deduction. And that means that this auto-ref will bind to everything. It'll bind to L values, R values, modifiable things, const things. And it keeps them alive because it's a named reference. And it doesn't do any copies. So this is great. This means if I've got a function that's returning a vector of int by value, then I can say for every int I in, and then call the func right there, and then go print out the I. And by storing it in this auto-ref range, I'm suspending that temporary in midair. I'm going to go back for the lifetime of this loop, and only when I hit this extra closing brace at the bottom will the temporary be destroyed. This is great. It makes your code way less verbose than what you would have to do with an iterator loop. There you would have to give the vector a name. You would have to say vector int v equals func, and then for auto I equals v begin, I now equal vn, blah, blah, blah. Or even worse if you were C++ 9003, for vector int iterator I equals, horrible. Now we can just say for int I in func. That's nice. And you don't need to worry about unnecessary copies. As for how we get begin and end from the range, the standard actually goes through a few cases. If you've got an array of n elements, the range-based for loop automatically knows how to handle that. The beginning of an array is just a pointer to the first element. The end of the array is the array plus its size. Then if it's not an array, the standard says, oh, if you've got a class with a begin and end member, then call .begin and .end. This case handles all standard containers and boost containers that have member begin and end. But it's even more extensible than that. If you've got something that's not an array and doesn't have a begin and end member, then it will try to call non-member begin and end and look them up through argument-dependent lookup. Now, I've called this slide sealed evil in a can because that whole argument-dependent lookup thing is kind of scary. Herb Sutter is not super fond of argument-dependent lookup legitimately because it's got scary gotchas. But fortunately, it's not used as long as you've got an array or a class with the begin-end members, which is the vast majority of types that will be used with the range-based for loop. This changed during the standards development, if you were following that closely. The standard iterator header actually has overloads, non-member begin end, that take arbitrary containers or built-in arrays. But these are precisely the cases that are never used by the range-based for loop. It has dedicated code to handle them. So these non-member overloads are still good for writing generic code that can accept objects of class type or arrays. But the range-based for loop doesn't depend on them. It did early in C++ OX's evolution, but not in the final C++ 11 standard. The one time I'll mention C++ CX in this talk is that range for does not know anything about Windows Foundation collections. If you want it to, you need to include the header collection H, which I also wrote, which provides non-member begin end. This shows you how things can be extensible without going and teaching the compiler about that. So, quick pop quiz. I've got the snippet of code that the for range declaration expands to. And what if I write a loop, say I've got a vector string, and I say for string s1 colon v1, and I assign to s1. Is that going to modify the elements of v1 in place? The answer is no. If you write this, what you get is a modifiable copy of the elements in the vector. Why is that? Well, the standard is literally rewriting this code to string s1 equals dereference some iterator, and everybody knows if you write that, you're getting a copy of the element. You can get a const copy if you say const string, but you're not looking at the element in place. That is not so good for performance, and if you are attempting to write to the vector, you're going to be like, hey, my writes were lost. Same would be true if you wrote for int I colon v. Now, if you write for string ref s3 colon v3, then you do get a reference bound to the element in place, and you can either observe or observe modify. So now I'm going to take the slide, and I'm going to replace the strings with auto. And what happens there? Well, if you say for auto element in vector, then you get a modifiable copy as before. If I say const auto, I get a const copy. If I say for auto ref, it's a little different. If the container is modifiable, I get a modifiable reference. If the container is const, I get a const reference. It compiles either way. But of course, it limits me if the container is const. I certainly can't violate const correctness. It may be a little confusing as to why auto is behaving this way, but it's all because of template argument deduction. I'm just going to skip over that, running out of time. So now, audience participation. I want you to vote, OK? Show of hands. I've got a vector in V, and I'm going to say either for const auto ref s1 in V or for const string ref s2 in V. One case I'm saying auto, other case I'm being very explicit about the type. Which one's faster? Raise your hand if you think the const auto ref is faster. Okay? Raise your hand if you think the const string ref is faster. Raise your hand if you think they're identical. Everyone thinks they're identical. You're right. They're identical. Very good. You're hired. Or you're not fired. Now, what if I switch this over to a map string int? Okay, I've got for const auto ref, or I can be very explicit and say for const pair of string int ref p2, because a map's elements are actually, its value type is a pair. Who thinks const auto ref is faster here? Okay, who thinks const pair, being explicit, is faster? Who thinks they're identical again? I'm trying to get you. Actually, const auto ref is faster. Man, I wanted people to vote for identical again. Why is const auto ref faster? Well, I thought I was being explicit about the pairs type. I got it wrong. The map's value type is pair of const string int. The key is const because you can't be allowed to modify the key which controls the representation of the data structure. That would corrupt it horribly, so it applies constness. Everybody forgets this. I forget it from time to time, especially if you try to customize the allocator. So if you write const pair string int ref, that's not the same type. You can still bind a reference to it, but what the STL will do, we just saw all of pairs converting constructors. It says, I've got to make a temporary pair. I've got to make a temporary pair string int and copy construct it from the pair of const string int, and that's going to copy a string. Oops, I'm incurring a copy for every element. If I say const auto ref, then I don't incur that copy. So my guideline is 95% of the time, you should just write for autoref e in range, or for const autoref e in range if you want to be very clear about I'm not modifying this thing at all. That's going to observe the thing in place. It's always going to get the right type. So why would you ever want to use anything else? I thought about it, and I can think of 3 cases. Maybe I'm missing some. But if you actually want to copy, maybe you want to modify it and then go pass it off to some function, then it's OK to say for auto e. Might be good to put a comment there saying, hey, I really mean to copy this. I'm not just a dummy and forgetting about the copy. Sometimes, and this is more obscure, maybe you want to copy and convert. Like you've got a vector of short, and you want to widen each element to unsigned long before processing it. Well, there you could say for uint64t in vector, and that will copy and widen. And most obscurely for the Boost developers in the audience, if you've got proxy iterators like vector bool, our most hated enemy in the universe, its iterators don't return actual bool references. They return a special object. And that won't work properly with autoref or const autoref for various reasons. But if you say for autoref e in range, again, that's a super magical omni reference that binds to everything. I would only expect to see that in highly generic code. Most of the time, just say for autoref or const autoref, and it'll work great. So if you have more questions, I've got a link here to the C++11 working paper. This is actually the first one after the international standard was shipped, but the only changes since it were editorial. This means it's equivalent to the official standard plus bug fixes, which is actually very nice, and it's publicly available. I've got a link there to my blog post about the C++11 features supported in VC11, but now you know when it says range-based for loop no, it's secretly yes. I'll have to go update that later. I've got a link there to VC10's concert documentation, which you can read about, or you can just go to MSDN and crack open the nodes. It's filed away under Visual Studio, C++ something. And if you have questions specifically about these slides, I've got my email address there. So let's take some questions.
Questions?
Perfect.
We have thousands of occurrences of the Microsoft extension for each.
Oh, that horrible, horrible thing. OK.
And so I would like to port them, and I'm wondering if you know of any gotchas.
The range-based for loop should be strictly better than the for each abomination. I am not aware of any gotchas that would be caused by converting the one into the other. The for space each extension is bad because A, it's not customizable. It doesn't do that cool ADL thing, and The other thing is that it has extreme trouble modifying elements in place. It never worked in VC9, and I believe it was broken in VC10. I think they might have gone and fixed it in VC11. Jonathan would know for sure. But attempting to modify elements, it's inserting crazy stuff that you can't see, like a const cast or a static cast. Horrible. The range-based for loop doesn't have any of that. I believe if you just convert it, your code will certainly not be broken more and may even receive bug fixes. Please stop using that extension. It's terrible. So bad.
More questions?
Got a question here?
Okay. Sorry, this is going to work this way.
This question is about type erasure. I remember that in Boost, they were just define that type erasure is a way to eliminate virtual table explosion. So when you're mixing templates, I noticed that you are not using that for that purpose. You're actually using virtual functions in shared pointer.
That's right. Type erasure can be accomplished either through virtual functions or through storing function pointers. I saw that note in Boost documentation. It's the same result either way, except one potentially introduces vtables. So far, we haven't seen the vtables causing any negative effects. If we do, we could switch to using the function pointers. But for now, the virtual functions are more convenient for us. It's an optimization we may apply in the future. Apparently, Boost considered it important enough to do.
All right, we have one here.
Bjarne had a question down here.
Bjarne has a question?
Yeah, just get to him eventually.
You know what? We'll do Bjorna and then this gentleman. So here, you can hold on to this for Oh, he needs a mic.
I'm getting it.
We have to move the microphone from one to another. If we could only place it in users' hands.
If you could, would you define capital NULL as null pointer?
That's interesting because the standard is actually, and I raised this on the committee's mailing list, it sort of defines the worst of both worlds now. It says the macro null may, but not necessarily is, either 0 or null putter. It doesn't guarantee 0 and it doesn't guarantee null putter, which is actually sort of the most inconvenient. So funny story, when we implemented null putter due to the pair debacle, I was actually under the impression at the time, and so was Jonathan, that the standard mandated switching the macro null over to null putter. So I went into the CRT's headers and I changed the macro, and then I tried to build just the compiler and libraries. I didn't even try to build the rest of the VS at the time. And I found hundreds of build breaks. People were misusing null left and right. This is where I found they were using null as a character constant because of NUL. Then I saw the more horrible things where they were just using it to initialize integers. It actually found some surprising bugs. But certainly it was not backwards compatible. Starting over from scratch, absolutely. I mean, the macro null should just be null putter or should be null putter itself. But as far as changing existing code, it seems like it breaks the world. Now, in the standard library, I love breaking user code so much. You have no idea. I break user code all the time. Like the C++11 made set elements immutable. They're now const. And that's actually a breaking change to C++ 9803 programs that thought, oh, I can modify this element as long as I don't change the sorting criterion. But adding constants there was just so important that we did it, and I didn't even include escape hatch. And yeah, it broke some programs, but it was for the good of everybody. When it comes to null, though, it just breaks so much code. I don't know. It's hard. Certainly would be nice if it was controlled by like a compiler option or something so people could migrate over. And I guess the standard does permit that. But it seems like enough work that we haven't done it in VC11.
All right, I got a question kind of on the t-shirt.
Oh, yes. The cool t-shirt code. No kittens. I would want to include me out there.
So I have a question. What if I really, really wanted to iterate over a collection of those futures in the order in which the futures were complete and available for getting?
You're not really notified when a future completes. Certainly, what you could do is in the Lambda, you could say, OK, when this Lambda gets to near the closing brace, then go have it add its result to something. One way is to have a vector and a mutex, capture both by reference, lock the mutex, push back into the vector, and then release the mutex with a lock guard. And that way, you'll get the results in the order in which they complete it. Which would be a little more code, and you would have to go take a lock explicitly. Alternatively, you could use a lock-free data structure. You could have your Lambda use a concurrent underscore vector from Concert, the parallel patterns library, and that allows concurrent pushback without taking any locks at all. And you would get the results in the order that they were produced. So that's how I would do that.
Great. Thank you, STL. STL, come on. Amazing.